In this video, we're going to look at a few more examples of the ratio test. Test the following series for convergence or divergence. Question A, summation n equals 1 to infinity, n factorial divided by n to the power of n. Question B, summation n equals 1 to infinity, n times minus 2 to the power of n, divided by 3 to the power of 2n plus 1. Question C, summation n equals 1 to infinity, negative 1 to the power of n, times 1.1 to the power of n, divided by n to the power of 10. Let's look at question A first. Here we have summation n equals 1 to infinity, n factorial divided by n to the power of n. Let's apply ratio test with a sub n is equal to n factorial divided by n to the power of n. L is equal to limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit n approaches infinity. Now we don't need the absolute value because everything is positive. N factorial in the numerator is positive and n to the power of n in the denominator is also positive. So plug in n plus 1 wherever we see an n. So we get n plus 1 factorial divided by n plus 1 to the power of n plus 1 divided by n factorial divided by n to the power of n. Now let's simplify this in such a way that we get easy cancellations. Limit n approaches infinity, we can rewrite n plus 1 factorial in the numerator as n plus 1 times n factorial. And in the denominator, n plus 1 to the power of n plus 1 can be rewritten as n plus 1 to the power of n times n plus 1. Now we're dividing by this fraction, that's the same as multiplying by the reciprocal. So that's times n to the power of n divided by n factorial. And now we get the cancellations. N factorial in the numerator cancels out with n factorial in the denominator. N plus 1 in the numerator cancels out with n plus 1 in the denominator. So we get limit as n approaches infinity, n to the power of n divided by n plus 1 to the power of n. This is equal to limit as n approaches infinity, n divided by n plus 1 to the power of n. Now we're going to rewrite this as limit n approaches infinity, 1 divided by n plus 1 divided by n to the power of n. Now divide through, do some algebra, we get limit n approaches infinity, 1 divided by n is 1 plus 1 over n to the power of n. Now this limit in the denominator is a special number e, so this is equal to 1 over e, which is of course less than 1, so the series converges by the ratio test. Now let me talk about this limit. So the limit as n approaches infinity, 1 plus 1 over n to the power of n, this limit in the denominator, this is equal to e. You can prove this by applying L'Hopital's rule and applying log function. You probably have done that in a calculus 1 course, differential calculus course. So in any case, the limit L is equal to 1 over e, which is less than 1. And if the ratio is less than 1, that means the series converges by the ratio test. So let's write that down. Since L is equal to 1 over e, which is less than 1, the series, the given series, summation, n equals 1 to infinity, n factorial, divided by n to the power of n, converges by the ratio test. Now let's look at question B. Here we have summation n equals 1 to infinity, n times minus 2 to the power of n, divided by 3 to the power of 2n plus 1. Let's simplify this first. So we have summation n equals 1 to infinity, n times minus 1 to the power of n, times 2 to the power of n, and splitting up this exponential in the denominator, we get 3 to the power of 2n times 3 to the power of 1. Simplifying a bit more, summation n equals 1 to infinity minus 1 to the power of n times 2 to the power of n times n divided by 3 to the power of 2n is the same as 9 to the power of n times 3. So we'll apply the ratio test. We'll apply the ratio test with a sub n is equal to minus 1 to the power of n times 2 to the power of n times n divided by 3 times 9 to the power of n. So L is equal to limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit as n approaches infinity. Now plug in n plus 1 wherever we see an n. So we get negative 1 to the power of n plus 1 times 2 to the power of n plus 1 times n plus 1 divided by 3 times 9 to the power of n plus 1. Now we divide by an, which is the same as multiplying by 1 over an, so we're just going to reciprocate this fraction. Times 3 times 9 to the power of n divided by negative 1 to the power of n times 2 to the n times n. So L is equal to absolute value of negative 1 to the power of n plus 1 divided by negative 1 to the power of n times n plus 1 divided by n times 9 to the power of n divided by 9 to the power of n plus 1 times 2 to the power of n plus 1 divided by 2 to the power of n. And of course, 3 cancels out. This 3 cancels with this 3. So simplifying it a little bit more, we get L is equal to limit n approaches infinity, absolute value of negative 1 times 1 plus 1 over n times 1 over 9 times 2, which is equal to, well, 1 over n, this ratio approaches 0 as n approaches infinity, so the result is 2 over 9, which is less than 1. That means the series converges, absolutely by the ratio test. So when you're doing the ratio test, you really have to be careful with the algebra of reducing exponents and canceling things out. That's where the errors can take place. So the algebra is really the most important part when you're doing the ratio test. It's a very mechanical type of procedure. Let's look at part C. Summation n equals 1 to infinity, negative 1 to the power of n times 1.1 to the power of n divided by n to the power of 10. We'll apply the ratio test with a sub n is equal to negative 1 to the power of n times 1.1 to the power of n divided by n to the power of 10. So L is equal to limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit as n approaches infinity, absolute value. Now plug n plus 1 wherever you see an n. So we get negative 1 to the power of n plus 1 times 1.1 to the power of n plus 1 divided by n plus 1 to the power of 10. Now we're dividing by an, which is the same as multiplying by 1 divided by an. So just reciprocate the fraction, we get n to the power of 10 divided by negative 1 to the power of n times 1.1 to the power of n. So L is equal to limit as n approaches infinity, absolute value of negative 1 to the power of n plus 1 divided by negative 1 to the power of n. And all the other terms are positive, so we don't need the absolute value for the other terms. 1.1 to the power of n plus 1 divided by 1.1 to the power of n times, and we have n to the power of 10 divided by n plus 1 to the power of 10. So if we simplify this, we're going to get L is equal to limit as n approaches infinity, absolute value of minus 1 times 1.1 times n divided by n plus 1 to the power of 10. Now let's take the limit as n approaches infinity. So let's just divide by the highest power, divide by n, divide by n, divide by n, and we're going to get L is equal to limit as n approaches infinity, absolute value of minus 1 is just 1 times 1.1 times 1 divided by 1 plus 1 over n, all to the power of 10. Now this ratio 1 over n approaches 0 as n approaches infinity because 1 over a very large number. So the result is going to be just 1.1, which is greater than 1. That means the ratio test tells us that this infinite series diverges. Since L is equal to 1.1 greater than 1, the series summation n equals 1 to infinity, negative 1 to the power of n times 1.1 to the power of n divided by n to the power of 10 diverges by the ratio test. All right, thanks.